the magic combination here to make it be up there and over here. Okay, so this talk is not like the other talk. It's not web stuff. It's messaging patterns with ZeroMQ. Now, the messaging patterns could be implemented in whatever messaging framework you want, but it just so happens that some things are easier to do in ZeroMQ because you don't have to have a broker or a standalone service for connecting all your things together. But you can make a broker with ZeroMQ if you really want to. I'm going to show you an a simple version of that. But I'm not going to show any code, and I won't break any demos. So I'm Nathan Smith. I'm just lead platform engineer at Analytics, and I mentioned earlier we are a data science software company, and so I think we do some interesting things. But this is we use ZeroMQ for messaging between our services, and so I've learned a lot while building the new version of our platform, along with my colleagues. So ZeroMQ in 100 words. ZeroMQ looks like an embedded network library, but acts like a concurrency framework. It gives you sockets that carry atomic messages across various transports like in-process, inter-process, TCP, and multicast. You can connect end-to-end, fan-out, hub-sub, task distribution, request-reply. It's pretty fast. Well, I mean, it's quite fast. So you can use it to build scalable multi-core applications on one machine, or you can use it to connect many machines together, or just machines from around the world together. Built as an asynchronous processing tasks, and it has a score of language APIs and runs on most operating systems. And the makers of it, the company is called iMatix, and it's LGPL-v3. So this blob of text was from the ZeroMQ guide, which is quite good, and I will have a link to it at the end. And if you're interested in ZeroMQ, it's actually not too difficult to read, and it's pretty humorous, and you'll learn a lot about messaging by reading it. So, some things to know. So I'm going to go over quickly a few ground things that you need to know before I can launch into the patterns. You don't really need to have a deep understanding of them, but yeah, most of this is necessary. Okay, so what kinds of sockets can you have? You can have hub, sub, rec, rep, dealer, router, push, pull, and pair. Hub and sub naturally go together. Rec and rep go together, but they're like synchronous versions, so you can only send one message from rec before you can get a reply back, and then the other way with rep, you can only send a message after you receive one. A dealer and router are like async versions of rec and rep. You can go as fast as you want and go in any order. And push and pull are kind of like a one-way dealer. So if you push from one, you should connect a push to a pull. You push from a push, and it lands over in the pull. And then there's also a pair, which you could use to like connect threads in a process or something like that. And the pair is exclusive, so you can only connect one pair to one other pair. Yep.
What's the difference then between hub sub and push pull or dealer router?
We will get into that. Okay. So I would like you, if you have any questions, just chime in at any time, but not too many questions.
Don't ask that question.
So, what are some valid socket combinations? You can do pub and sub together, like I mentioned. And so this is a way to connect a set of publishers to a set of subscribers. So you can think of it as a person standing on a hill and a bunch of people around him, and they just shout and everyone hears it at the same time. So it's a good way to get a bunch of data out fast, but they can't talk back. Rec and rep, I mentioned, are like a synchronous request reply pattern. Think of it like an RPC. You can combine a rec and a router, and so you can think about a router like a server, where you have a bunch of clients who are interested in only asking for one thing at a time. The server can serve a bunch of clients at the same time. Dealer and rep. So you could think of it as the flip of that, where you have a client who's super chatty, and then maybe there's a bunch of things that they're talking to, but each thing can only do one thing at a time. And then there's dealer and router, fully async request reply. You don't have to go in any order. You can send from one to the other. Although there are some caveats with that. You have, if you're going to use a router, you have to know the address of the dealer that you want to send it to. You can use dealer and dealer together, and there I'll get into what dealer does in a little bit, but it's a valid combination. There are some situations where this is desirable. Router and router is somewhat similar, but you have to kind of aim even more carefully. You have to know the IDs of places where you want them to go. Push and pull, fan out, fan in pattern. And so you would use this if maybe you think about a pipeline where you need to send kind of work over this way and that way, and then they do stuff and they rejoin sometime in the future. And then pair and pair. I haven't actually used this one yet, but I'm sure it's useful for something. Messages. So what you actually are sending are called messages, and they consist of 0 or more frames, where a frame is just a blob of binary. So in Node.js, frames are buffers. In other languages, they are implemented as other data structures. Inside of this binary blob, you can put whatever you want. And so it's up to you to handle the encoding and decoding. But it lets you get as small as you want to introduce the complexity into your application. And then it's up to the designer to define the message protocol. Messages must fit into memory. And then a thing that's useful is after you've developed a set of protocols, typically you would just implement them in a library to help with the serialization and deserialization. Any questions on messages? I'll show an example in a second. But at Analytics, we have a suite of protocols that we use. Rec and rep are pretty much what they sound like. Error is like a rep, but it contains an error. Object, rec, and rep are really just bare bones. Only the information you need for an authorization check. But in the rec and rep, you can show it. Event is just a generic event container. And then we have some other things for if we're doing streaming messages, which are kind of like direction events. So here's an example of a protocol, the AU rec protocol that we use. And so over here, what you're looking at, you see the pre. Typically, you won't set anything in pre, but as they go through proxies and stuff like that, things might shove frames onto the beginning so that it knows how to get back to where it came from. And so that's one nice thing, since there isn't a centralized broker, in order to know how to get back to somewhere, even if it's several hops away, it accomplishes this by pushing IDs onto the message, and then as it comes back, it just pops them off. And then each thing along the way has a map of ID to connection. And then what we tend to do is we have a frame that denotes the protocol, so that's an easy 0 for parsing out the message. And then for rec, we typically use it for RPC commands. So we would denote the service that it wants to go to. If it was going through a broker or something, you could use that to switch. And then the command, so telling it what to actually do. And then this, for niceness, headers for some metadata, and then a body. And then the body can be whatever you want, but we typically kind of follow HTTP paradigms. And typically we'll just send JSON, but you could do BSON or message pack or protobuf or whatever you wanted. And then one last thing. Either side may bind or connect. There are no designated server socket types. Binding and connecting need not occur in that order. Sockets will automatically reconnect, and queued messages will start sending upon a successful connection. Yeah.
Can you explain binding and connecting for those of us who are
So
plebeians?
I mentioned that you can use various transports, but if you think about like in the web paradigm, where you have like an HTTP server, you typically bind to an interface on the machine where it's running, and then a port. So if you're just doing a generic HTTP, not SSL, then you typically bind to port 80, or if you're doing SSL, it's port 443. Here, if you're binding, you just have to declare what interface you want it to be on and what port you want it to be bound to. If you're doing other transports like IPC, then you would just give a path to a socket file on a local file system, or whatever the transport requires. And then when you connect, you just need to know the address, or an addressable version of the thing that was bound to. So if you bind to like 0000 port 8000, that means you're binding to all interfaces at port 8000, and then anyone who has maybe the IP address or the IPv6 address or a domain name or something like that could use all those to connect to the same thing. So any other questions before we launch into some patterns? So keep in mind what these various sockets do, because they're kind of important. So some basic patterns. I think this one is the easiest to get. It's probably the closest to like HTTP, where you would you make a request out to a server and it gives you something back. And so some things to know: the rec and the dealer sockets, they will distribute using round robin. So if you're connected to multiple, so if a rec is connected to multiple reps, it would round robin. So you send, receive, send, receive. A dealer, you could just fire them off and it would just go in a circle. A rep can only receive one message at a time, pending your reply. The router interleaves messages from clients. And then, well, actually, anything that receives messages will just interleave them. So whatever order they come across the network, that's the order that they'll be delivered to your code. And then messages queued in the sender. Messages are queued in the sender and persist until a connected recipient, until someone connects to you, at which point it will send it, or you reach your high water mark for the queue, in which case it will start dropping new messages. So set your high water mark accordingly.
What's the high water mark?
It's how large your queue can be before you start dropping messages. Because remember, all messages have to fit into memory. So
Because there's no broker, correct?
well, I mean, you could persist them to disk. It's just if you have sent it and you're not managing the actual sending of it, it will go into an internal queue in the worker threads. Or the socket is killed. So if you don't persist them somewhere and have a way to replay them and your socket dies or you kill it, then all queued messages are gone. That's everything I just said. But it's there in case you want to look at the slides later. Publish, subscribe. So if you've done any socket I/O work, this might be a little more familiar to you as well. Typically, it doesn't, like I said, either side can bind or connect, but in the most basic case, you might bind the pub and then connect a bunch of subs. And then the subs can set subscriptions and then only receive messages that where the first frame does a prefix match on the first frame. And so if you're subscribed to topic ABC and a message comes through that's ABC123, you'll get all messages for that. And so something that's good to remember is topic organization and separation is important. So what I typically do is I'll separate topics with some delimiter, like a semicolon or something like that, so that if you're publishing events about places, maybe you wanted to only care about ISB and that's our organization structure. If you set that, you would only get things related to ISB, and then the semicolon denotes the end of the topic, so you don't match like ISB dash blah. Or if you wanted everything for USA, you could just say USA, semicolon, and then you get everything related to that. Publish and subscribe is subject to the slow joiner syndrome. And so if you have a publisher who is publishing things pretty fast, there is a certain amount of time. It's non-zero amount of time that's needed for connection before you'll get your first message. And so typically if you're joining, you'll miss the first few view. So don't be surprised at that. And then it's really keep up or die. So if your publisher is super overpowered and your subscribers are really underpowered, they may fill up their incoming buffers. So keep up or die. And then if you're actually using this, a tip is to remember to set the subscription to just like an empty string or something like that, so that you'll receive all subscriptions. Because if you don't set a subscription, you won't receive anything. You'll be really confused. And you can have multiple subscriptions. And then the pipeline, push sends using round robin, pull interleaves incoming messages, and then outgoing messages are again queued in the sender. And so what this would do is say there's work in the ventilator, and then a set of workers for which the amount of work to be done is greater than you could do maybe processing one message at a time. Then you might fan out to the various workers and they can do stuff, and then they can push the results to the sync. So, any questions on those kind of primitive patterns? Okay, well, let's get to something a little more interesting. So, let's say you have a client and you don't want to just connect to one worker. Let's say you have a set of workers. Yeah. So we could do the push-pull method that you just saw. But what if you want data back from the workers? Well, you could set up a push socket and then a pull socket, and then you could push messages to workers, and then workers could push them back to you. But you could also use like a dealer to rep. And so what this pattern would do is the dealer would round robin them to the workers, and hopefully you don't have more than 3 tasks at a time, because otherwise they'll just queue up from the dealer. And so it would send it to the first worker, and then it would go do its thing, and then send it back. And in this particular setup, workers can only do 1 task at a time. So what if all the workers are busy and you need something done right now? That this particular version can't accommodate that. But what if workers could have the capacity to handle multiple tasks simultaneously? This also is blocking that because it uses a rep there. Again, any questions, just chime in.
Can you remind us of a rep is a synchronous single receiver?
Synchronous, it receives a message, does stuff, and then sends one back. You can't send until after you received.
You can't receive again until after you've sent?
Right. Yep. So the difference here is we switch all the reps out for routers, and now what happens is that as fast as the client sends messages out, it'll just round robin between them, and then the workers will just keep getting work, and hopefully they can keep up. But then the question is, what if there's too much work? Yeah.
So you mentioned in the previous example, if there's too much work here, they queue up on the dealer side,
yep.
Correct? So maybe you're about to answer that then about what happened. Will they then queue up on the router side here since they've been sent by the dealer?
Yeah. So if your worker thread is blocking, then they will queue up in the socket and then get delivered. But if your client is a lot faster than all of your workers, then it's possible that you could saturate your workers and they could die, or they could. I mean, it depends on how you code it, or you could just start losing messages. But you could always add more workers if you wanted to. But hopefully you don't have more than 1 client. Or hopefully you have enough workers to keep up with the amount of clients that you're expecting. Now, you shouldn't confuse the boxes here to represent the maximum capacity of message handling of a particular application. People's applications there's a wide variety of workloads. So it may be that processing a message is super fast, or maybe kicking off some work that will take an hour. It just depends. It's just representative of the pattern. So in this particular scenario, think about binding and connecting. If you could have the workers bind and the client connect to them, but then that suggests the question that how does the client know where the workers are? Do you have to hard code that into them, or do you have to get that information from somewhere else? You could flip that around. Of course, the dealer could bind and workers could connect to that, but then workers would have to know where the client is, or what if you want to have more than one client, where workers have to know about all the possible clients? And then in addition to that, what if you were to add, let's say the workers are binding, the client connects to them, you add a new worker, how does the client know where the new worker is located? So, a natural solution to that is to have a dedicated balancer. Now this kind of looks like a broker, but it's kind of a compromise, because now you only have one address to remember for all clients to connect to send messages to. And then the balancer just bounces them off to workers. And so this diagram is actually kind of interesting, because if you notice the workers, instead of having reps, they have recs. Does anybody have any idea why they would do that?
They pull. They're asking the router for work, like thread pool would work. Exactly.
So they say, I'm ready, and then when it has a message for them, it will give it back.
So in this case, the balancer would bind on both sides, so that would bind both in the client and worker side, so that both the client and the worker could then be the connectors.
Yeah, that's probably what you would do. Typically, you want to bind on whatever the most stable, long-lived part of your architecture is. So the thing that's going to stick around the longest, that's probably the thing that you should be connecting to. So here we have a single dedicated endpoint, or a few of them that clients can easily know about. And then we're just going to call this a balancer. But what if all the workers are busy? So in this particular diagram, if you have 3 workers, you can only do 3 things at a time. Should the balancer queue indefinitely? Because that's what's going to happen. It's just going to wait in the balancer until a worker finishes its task and says, more please. And what if you have some sort of SLA? What if you have a max lifetime on a request? And you need to have it done within, say, 5 seconds, otherwise you need to know if it failed or not. And then what if workers could handle multiple tasks simultaneously? We asked that question before, and we accomplished that by swapping them out for routers previously. But in this next one, we swap it out for dealers. So now the workers still ask for work, but they can ask for as much work as they want. So they could say, give me 4 works, and then they don't have to ask for any more. It depends on how you set it up. So because all of this, the protocol of the messages that you send is really up to your application. So I'm overloading the protocol term here because I used protocol to define the format of a message previously, but protocol could also apply to the sequence of kind of named messages or message types that you send. And so if you define one message type as a work request, you could request for 4, like let's say a worker could do 4 things at a time, could send 4 work requests, and then when it receives a work command to be done, then it could do that and then keep track of how many it has out at any given time and then send a new one out. Yeah.
So because these are dealers on the bottom, did you go all the way back up that with your response?
Yeah. So that's a detail that you would get if you were looking at the Z guide. But what happens is when you have a request come from the client, let's say the dealers connect to the router, there is an ID for the top client interface. You can either set it or it can be auto-generated. And the router keeps the ID mapping back to the client socket. And so when a message comes into the router, it will push the ID onto the front of the message, and then the dealer doesn't add any IDs, and so it doesn't get changed at all. And so one thing that this does apply is that workers can only be connected to one balancer at a time. Because if you send it back, and then it gets, if you had multiple balancers and it got back to a router which wasn't connected to the particular client, it wouldn't be able to send it back to wherever it came from.
The one thing I'm confused on is it seemed like dealers were supposed to be senders, generally speaking, but the workers are dealers in this case, and I'm a little confused at.
Yeah, so you answered the question.
Oh,
last frame
they were at.
Why they were right.
Then why is the? Can we go back to the? Then why was the balancer, the bottom part of the balancer switched to a dealer and not?
To a dealer, because now it'll just round robin between them.
If the workers are requesting it, the workers are the ones initially sending requests for work, then why would the bottom of the balancer?
So in this one, if a worker requests work, then the router will append or will push the ID onto the front of the message, and then it keeps that somewhere, and then when it's ready to send work back to it, it'll just take that ID so it can go back to whoever requested it. But in this one, but actually you are right. You could.
It just seems like you have a sender talking to a sender. That's what I was confused about.
Yeah, you're right. There should be a router in this case. So in this case, what it would do is the dealer would ignore their work request. So you're right.
If you, so when you're using the IDs to go back up the chain to the beginning, if you knew that like multiple balancers were all connected to all the same clients, could you then have multiple balancers since it wouldn't matter what balancer you send it to, because they would be able to then use the ID to get back to the right client?
Sure.
I don't know if you would want to do that at all, but.
Yeah, you could also change the workers to routers, and then you could use, if you had those as routers, you could have the bottom one of the balancer be a dealer, and then the routers would put the ID of the balancer that it got it from to the message, and then it would send it back to the right balancer. But if all the balances were connected to all the clients, then it wouldn't really matter if you wanted to use this scheme. Okay, so then the question is, what if there's too much work in this case? If you're distributing using the dealer, well, okay, so that's another thing. The workers don't have to ask first. They can receive in any order. One reason that you might want to use a dealer is because it doesn't do the ID frame business, so you don't have to manage that. And so you could just have them not ask for work and you could just send it to all of them as fast as you wanted. But in which case it comes back to the same question, what if there's too much work? Or what if you have varying capacity, or they could service multiple workload types of varying duration at a time? So slight difference here is now you have routers connected to routers. But this implies that you need to know the IDs of the workers ahead of time, or they have to register via some other means that's not shown in this particular diagram. And so in this one, you are free to make up whatever distribution algorithm you want. And so you could implement like a used, or you could have a capacity round robin, or you could, you could weight workers depending on their hardware capabilities or things like that, whatever you want. But you have to, this one is also kind of the most manual, because you have to implement an algorithm and then also monitor worker availability. And so this comes to something similar to a balancer that we made for our product called OnSite. And so we have basically workers come online, they talk via their manager interface to the delegator there, or to the balancer, and they register themselves with the balancer, and the balancer puts them into a pool, and then we have various algorithms that we can use depending on the worker capacities and stuff. But if they're all equal and they can handle more than one request at a time, then we'll typically just do a capacity-based round robin, where let's say a worker can do 5 requests at a time, and then they'll just round robin worker A, B, C, D, and then work with the completion would come back over time, and then the capacity would keep getting added back to the workers. And then the workers also heartbeat to the balancer. And if the worker fails to heartbeat for a certain amount of time, it'll stop trying to distribute to it. So that is the end of, well, no, there's one more, of the load balancer. So this one's kind of interesting. It's not using the request reply things anymore. Does anybody see what this is doing?
Blasting work out to everyone.
Basically, it's
like workers fight for it.
Exactly. It's saying, here's work. Whoever gets back to me first gets it. So the messages come in from the client. It blasts it out on the pub. Whichever worker is available sends a message via some management interface, and then the balancer can send the work description to it back as